Welcome to this fascinating journey into the architecture of animal life. Today, we are going to explore two of the most revolutionary upgrades in evolutionary history, the coelom and metamerism. If you have ever wondered how a soft, squishy earthworm can push its way through hard, packed soil without being crushed, you are in the right place. We will build our understanding from the ground up, looking at the biology, the physics, and the math behind these incredible adaptations. Let us dive in. To start, imagine packing fragile glass vases into a box. If you just throw them in, they will shatter. But if you pack them surrounded by water balloons, they are safe. In animals, the fragile vases are our internal organs, and that protective water balloon is the coelom. Biologically, a true coelom is a fluid-filled cavity between the outer body wall and the inner digestive tract. But what makes it a true coelom is that it is completely lined by a specialized tissue called the mesodermal epithelium, or peritoneum. This lining forms flexible bands called mesenteries that hold organs securely in place. Animals with this true cavity are called eucoelomates. Now that we know what a coelom is, we must ask, why did nature invest so much energy into creating it? First, the fluid inside acts as a brilliant shock absorber, protecting delicate organs from sudden impacts. Second, it creates a hydrostatic skeleton. Because fluid cannot be compressed, soft-bodied animals can push against this fluid to move their bodies. Finally, and perhaps most importantly, the coelom provides a spacious, dedicated compartment. This allows complex organs, like a beating heart or expanding lungs, to move and grow completely independently of the outer body wall. Without this space, large and complex animals simply could not exist. This brings us to the mechanics of how animals actually use this fluid-filled space to move. We can model a single segment of a worm as a simple cylinder. The formula for the volume of this cylinder is V equals pi times r squared times L. Here, V is the total volume of the coemic fluid, r is the radius of the segment, and L is its longitudinal length. Because the coemic fluid is essentially water, it is incompressible. This means the volume, V, must remain absolutely constant. If the animal squeezes its circular muscles to decrease the radius, the length must increase proportionally to compensate. This is the fundamental mathematical principle behind how a worm stretches forward. Let us see this formula in action with a concrete example. Imagine an earthworm moving through soil. We are given a coelomic segment with a constant volume of 314 cubic millimeters and an initial radius of 5 millimeters. The worm contracts its muscles, shrinking the radius down to 2 millimeters. We need to find the new length. Because the fluid is incompressible, we rearrange our volume formula to solve for the new length, dividing the constant volume by the new cross-sectional area. Plugging in our numbers, we divide 314 by pi times 2 squared, which is 12.56. This gives us a final length of 25 millimeters. By simply squeezing its body, the worm has dramatically extended its length to thrust through the dirt. Now that we have calculated the final length, let us formally prove why this extension happens by looking at the underlying algebra. We start with the biological fact that the volume before contraction must equal the volume after contraction. We write this as the initial volume equals the final volume. Substituting our cylinder formula on both sides, we see that pi times the initial radius squared times the initial length equals pi times the new radius squared times the new length. By canceling pi and isolating the new length, we reveal a powerful ratio. The new length is proportional to the square of the initial radius divided by the square of the new radius. This proves mathematically that even a tiny decrease in radius results in a massive increase in length. Having proven how the coelom functions mechanically, we must now ask how it evolved historically. Biologists have two main theories for how solid-bodied ancestors developed this cavity. The first is the schizocoel theory, which suggests that solid blocks of mesoderm tissue literally split open to create a hollow space. We actually see this today in the embryos of annelids and arthropods. The second is the enterocoel theory, which proposes that the coelom formed from pouches that pinched off from the primitive gut lining, a process seen in chordates like us. While the developmental paths differ, both evolutionary routes achieved the exact same brilliant result, a functional, fluid-filled internal cavity. This brings us to our second major evolutionary leap, metamerism. Think of a long freight train made of dozens of identical boxcars. If one boxcar derails, the rest of the train can often keep going. Nature used this exact same modular blueprint, which we call metamerism or segmentation. Formally, it is the serial repetition of similar body segments, called metameres, along the longitudinal axis of an animal. In a truly metameric animal like an earthworm, this is not just skin deep. Internal structures like blood vessels and nerves repeat in every single segment. Crucially, these segments are physically separated from one another by internal walls of tissue, known as septa. Why did nature adopt this segmented boxcar design? The evolutionary advantages are massive. First, it provides biological redundancy. If a predator bites off a few segments of a worm, it can survive because the remaining segments contain duplicate vital organs. Second, those internal walls, the septa, isolate the coelomic fluid into watertight compartments. This allows the animal to contract muscles in just one specific segment without affecting the fluid pressure anywhere else, enabling highly precise movements. Finally, metamerism paved the way for tagmatization, an evolutionary process where segments fuse together to perform unique tasks, eventually forming distinct heads, thoraxes, and abdomens in advanced animals. To truly appreciate the mechanical genius of metamerism, we need to look at the physics of burrowing. When a worm digs, it must generate high internal fluid pressure. This creates tension that threatens to tear its body wall apart. We model this using Laplace's law, written as T equals P times R. Here, T is the tension tearing at the body wall, P is the internal hydrostatic pressure of the fluid, and R is the radius of the fluid compartment. This formula tells us something critical. The tension on the body wall is directly proportional to the radius of the fluid compartment. If the radius increases, the tearing tension increases right along with it. Let us apply Laplace's law to a concrete example to see which evolutionary design is safer. Imagine two worms trying to burrow into hard soil, which requires generating a high internal pressure of 100 pascals. The first worm is unsegmented, meaning its entire body is one giant fluid cavity with a large radius of 10 millimeters. The second worm is segmented, so it can isolate a tiny compartment with a radius of just 2 millimeters. We multiply the pressure by the radius for each. For the unsegmented worm, 100 times 10 gives a massive wall tension of 1,000 units, which might cause it to rupture. But for the segmented worm, 100 times 2 gives a tension of only 200 units. Now that we have seen the numbers, let us formally prove why metamerism is a revolutionary adaptation for burrowing animals. We want to establish that segmentation always reduces body wall tension for a given burrowing force. We start by setting P as a constant, required burrowing pressure. The tension for the unsegmented worm is P times its large, undivided radius. The tension for the segmented worm is P times the small, isolated radius of a single metamer. Because the internal septa prevent the fluid from bulging out, the effective radius remains very small. Mathematically, since the small radius is strictly less than the large radius, the tension in the segmented worm must always be less than the unsegmented worm. Continuing our proof, let us look at the exact ratio of these tensions. If we divide the tension of the segmented worm by the tension of the unsegmented worm, the constant pressure P cancels out completely. We are left with the ratio of the small radius to the large radius. This mathematical result is profound. It proves that the tension on the body wall scales linearly with the compartment radius, completely independent of the pressure required to dig. By evolving internal septa to divide the body into smaller compartments, early animals figured out how to generate massive burrowing forces while keeping the mathematical product of tension safely low. This is the true mechanical power of metamerism. So, how did animals actually become segmented in the first place? The most widely accepted explanation is the locomotion theory, proposed by evolutionary biologist R.B. Clark. Clark argued exactly what we just proved mathematically. Metamerism evolved specifically as an adaptation for burrowing through heavy marine mud. By dividing the coelom with septa, early worms could generate high, localized pressures without rupturing. Another older idea is the fission theory, which suggests segmentation arose when an ancestor tried to reproduce asexually, but the chain of clones failed to separate completely. Today, however, Clark's locomotion theory remains the most mechanically sound and widely taught explanation. Let us bring all of these concepts together visually. On screen is a schematic diagram of a metameric animal. Notice the vertical lines separating the segments. These are the septa. The central segment is highlighted to show the isolated coelomic fluid. The outward-pointing arrows represent the internal hydrostatic pressure, P, pushing against the boundaries. The vertical arrows show the small isolated radius, R. Finally, the horizontal arrows along the top and bottom represent the wall tension, T, trying to tear the tissue. Because the septa lock the fluid into this small compartment, the radius stays small, keeping the tension arrows manageable even when the pressure arrows are huge. This diagram perfectly illustrates the evolutionary genius of the segmented hydrostatic skeleton. We have covered a lot of ground today, so let us summarize the most important ideas. First, the evolution of the coelom provided animals with a protective, fluid-filled space for complex organs to grow, while also acting as a basic hydrostatic skeleton. Second, metamerism took this invention a step further by dividing that fluid into isolated, manageable compartments using internal septa. Finally, as we proved with Laplace's law, this segmentation allowed animals to generate massive forces for precise locomotion without destroying their own bodies. Together, these two architectural upgrades laid the structural groundwork for the incredible diversity of advanced animals we see on Earth today. Great job following along with the math and the biology.